organizations and return all of you.
Thanks, Dave. And my thanks to the organizers for the invitation to speak here. It's a great honor. And thanks to everybody for showing up. I gave a talk in last week's mini workshop, The Connections with Women. There will be a little bit of overlap just because, well, the title's essentially the same. But I'll try to say enough different stuff that if you happen to be here last week, it'll still be interesting for you. Also, I'm going to do what I can to target grad students as my focus audience, which means, of course, as always, that I assume you all know everything I've ever heard of any grad student ever knowing, plus a bunch of stuff that I wish someone had told me when I was in grad school. So, my goal for these two lectures is to illustrate the idea and possibly around brackets. Potential definition of what we might call non-commutative desingularizations, whatever those are, with some concrete examples. So as I say, the focus really will be on the examples and what we should hope for. Oops, where do my brackets end? There we go. There. Out of a definition from those examples. So the first motivating example, I want to talk for a little bit about the Mackay correspondence, or what you might call the maximal Cohen-Macaulay or Auslander-Mackay correspondence. So the setup is pretty straightforward. I want to let S be a power series ring over a field. I'm going to go ahead and assume that K has characteristic 0 just to make my life easier. I'm going to take a finite subgroup of the general linear group acting on S in sort of the obvious way by changes of variable, and I'm going to let R be the ring of invariance. And, well, so some first notes, observations in this situation is that R is a particularly nice ring. It's a complete Cohen-Macaulay normal domain. Well, I guess I should assume n's at least 2 or everything is terribly, terribly boring. Complete Cohen-Macaulay normal domain. My favorite kind of ring. And secondly, S is maximal Cohen-Macaulay as an R module. By which I mean that it has, well, the most compact way to say it is that its depth is n. If you didn't know what maximal Cohen-Macaulay meant, then this doesn't help you. Maybe one easy way to think about it is that S is finitely generated and free over a power series subring of R. And this second observation is why I care about this setup. My goal, so that's the big goal for the talks, but my goal in this example, my entrance into this, is to understand S as an R module, since it's in some sense a God-given maximal Cohen-Macaulay module. If I just hand you a random, say, Cohen-Macaulay normal domain and ask you to produce for me maximal Cohen-Macaulay modules so I can study them, because that's the kind of thing I like to study, you probably can't come up with one, other than the ring itself, which is sort of dull. But there are a few situations, and this is one of them, where because from the very construction of the ring comes equipped with Cohen-Macaulay modules, which I would like to understand. Yes, of course it is. It is, but it, in some sense, dull from the representation theory point of view as a Cohen-Macaulay module. Yeah. I mean, so in general, you can, if I ask you for Cohen-Macaulay modules, you might hand me the ring. You might also hand me the canonical module. Outside of that, there really isn't a source of these things in generality, but here's a source. So I want to understand S as an R module. To study S, introduce, as has been done in a few talks already, the so-called twisted group ring, which I'm going to write like this, S hash G, also known as the, I think Paul called it the semi-direct product, or the smash product. What this is the free S module on the elements of the group. So just like the usual group ring, with twisted multiplication. So if I've got, say, S sigma and I've got T tau, the result should be a multiple of sigma tau. But to get there, I have to move this sigma past this T, and that means that I apply sigma to T. So the reason one wants to study the twisted group ring in general is that a module over that twisted group ring, and I'll be a bit sloppy about whether I mean left or right, I won't worry about that, is nothing but an S module with a compatible action of the group. In particular, S is such a thing, and so understanding S as an R module, perhaps this is not immediately obvious how to do, but understanding S as an S hash G module might be easier and might give more insight, and it will, as we see shortly. An easy computation is that HOM over this twisted group algebra. So if I've got two modules, which are S modules with G action, HOM between them is the same as just looking at HOM as S modules and then taking the G fixed points. This is, well, in some sense, this is just a rephrasing of the observation above. And because I've assumed the characteristic is 0, this means that taking fixed points is exact. And so this isomorphism or equality extends to the higher x as well. So computing x over this S hash g is just taking x over s and then taking fixed points. Among other things, that means that the global dimension of this non-commutative ring, S hash g, is the same as that of S. Well, actually, that gives you one inequality. The other inequality is the causal complex. So this is a jazzed up version of S. It's still nice in this way, but it contains the information about G. Now, remember that I said I wanted to understand S as an R module. Here's where it comes in. There's a natural map, which I guess I'll call gamma, from this S hash g to endomorphisms of S as an R module. And this is actually just a really, it's so dumb it's hard to write down. What do I send in little s times a sigma? Well, sigma is an automorphism of S. It's acting on S. So really what I send S sigma to is S sigma as an endomorphism. And notice that since R is exactly what's fixed by sigma, this is R linear. Now this map is not in general isomorphism, but it is under a relatively mild condition. This is a theorem due to Auslander. Which is that if G is what we're going to call small, meaning contains no elements, non-trivial elements, I should say, fixing a hyperplane pointwise, then gamma is an isomorphism. These things are called pseudo-reflections. Since G is assumed to be finite, they have finite order. If they had actual order 2, we would call them reflections, but they might have bigger order. Oh, and I actually forgot to say, map here, what is map? This is a ring homomorphism. And it is a ring homomorphism precisely because we had the presence of mind to think ahead and twist the multiplication. So that's why that's actually there. So from Auslander's theorem, already, we can say something about the title of the talk. So from now on, just so I don't forget, we're always going to assume G is small. Then the corollary of Auslander's theorem, which is kind of a funny statement, is that R has a module finite algebra namely this one, which has 2 incarnations, which is, or which has, should we say, finite global dimension. And I'm not going to finish the sentence. Because what I want is to understand what would be profitable to put in the blanks. So I mean, there are lots of things you could say about this S hash G. I'm sorry? Oh, it just means finitely generated as an R module. Because it's finitely generated as an S module and so forth. So the question that I want to raise concerning these dots here is, what should those dots mean or stand in for if we want to call this thing a non-commutative desingularization? So this is a bit of overlap with my talk from last week. Let me run away from it now. Let's see what else we can say about S that might fill in the dots. Let's make sure I say these things in the right order. So we have this gamma, which is up above. Let me write it like this. This slightly dumb map gamma, which is an isomorphism because we're assuming smallness. But also, there is a map. And here's where we start to take advantage, really, of having a group here, or more generally a Hopf algebra, I guess. There is a map from S hash G to, that's supposed to say op, the opposite ring, where I send an element S sigma to sigma inverse with coefficient sigma inverse of S. And this is also an isomorphism. And as soon as you see an opposite ring in this context, and you've got end on the board already, you should realize that this is the same as the endomorphism rings, or endomorphism ring, excuse me, of S hash G over itself. And here is a place where I'm being sloppy. If I were talking about left modules, this would be endomorphisms acting from the right, but let me not worry about that too much. And this, of course, is also an isomorphism. And we can complete this diagram in an upward direction with a map I'm going to call rest. Where rest means I'm supposed to take an endomorphism of S hash G and restrict to get an endomorphism of S. S sits inside as multiples of this idempotent. This is actually the fixed ring of S hash G under the natural G action, but I'm not too worried about that. And so the corollary then is that these are all isomorphisms. so, what's the point? Remember, my goal is to understand S as an R module. The very first thing you might ask about S as an R module is, does it decompose? Is it a direct sum of littler ones? Almost certainly. How do you tell that? You look for idempotence in here. Oh, but that's the same as this. So let's look for idempotence in there. If we look at idempotence in the right-hand side, we get, which way do I want to say this? Projective S hash G modules are the same thing as what gets called add of S. So this is, these guys are direct summands of direct sums of S hash G. These guys are direct summands of direct sums of S. So all of the indecomposable summands of S as an R module are essentially the same thing by this diagram as indecomposable projectives over S hash G. If you prefer projectives to maximal Cohen-Macaulay modules, boom, there you go. And the map, because this is as I said, this version of S sitting in here is just the fixed ring of S hash G. The map going back and forth takes a projective to the fixed points of P. Okay, but so maybe you don't like projectives. I can't imagine. But maybe you don't. There's one more piece. Actually, there are several more pieces. I'm going to talk about one more piece of this puzzle, which is the representation theory of the group itself. So let's say the representation theory of G is also involved via, well, let's see, what can you do to get from a representation of G over this field K? Maybe I've got something called W, it's a representation in there. I can go from there to a projective S hash G module by tensoring over the field K with this ring S. So remember, an S hash G module is nothing but an S module with a G action. And here I've got S module, G action. The G actually acts diagonally here. And that Ext calculation, which is long gone, actually says that being projective is the same as being free over S. And then I can compose with the map on the left board, just taking G invariant. So this is in some sense the covariance, the module of covariance. This one over here I wrote equals. This is actually an equivalence of categories. That one over there, this composition is not. This is a mistake that many people have made, including me, that the Hom sets over here are finite dimensional vector spaces. Hom sets over here are not. Can't be an equivalence of any kind of categories. But it is at least a bijection. On objects. So if you are the sort of person, maybe you are a 19th century mathematician and you understand the finite dimensional representations of these groups G, then I will come to you and ask you questions about S as an R module and you will know the answers. Right? You will know the answers. Yeah, you will. All right. Let me specialize now. All of this has been in sort of arbitrary dimension. N was at least 2. When I wrote down the phrase Mackay correspondence, you may have steeled yourself for a lengthy discussion of something happening in dimension 2. Part of the point of giving this part of the talk is that all of this works for any n, but let me now specialize to n equals 2 and tell you how much better life gets, because it gets an awful lot better. So first thing I want to say is theorem of Herzog from 1978, which is that the Maximo-Cohen-Macaulay modules, which I'm going to write like this, Maximo-Cohen-Macaulay modules over R are in fact the same as this add S. So we already said that we always get containment one way. That means S is a Maximo-Cohen-Macaulay R module, and there's, did I goof it? Yeah, of course, I'm sorry. Thank you. Thank you. S is a Cohen-Macaulay R module, and so there's a containment this way. The point is that in dimension 2, you get them all. So this idea that I was talking about before, that there's something about the setup here that gives you some interesting Cohen-Macaulay modules in dimension 2, it gives you all the Cohen-Macaulay modules. So in particular, R has what I'm going to call finite Cohen-Macaulay type. That is, only finitely many indecomposables up to isomorphism. There are only finitely many indecomposable summands of S as an R module, so there are only finitely many of these guys. Which actually is the point at which I entered the story. I got interested from this point of view as a source of rings of finite Cohen-Macaulay type. And so let's just spell out what we've got in this case. If n is 2, which, oops, has vanished, but was just hiding. If n is 2, there are finitely many indecomposables Cohen-Macaulay modules, which, by the way, because n is 2, that's the same as reflexive. Let's give them names. Let's call them M1 up to M, I don't know, L. And a ring that I'm going to start calling lambda, which is the endomorphism ring of the direct sum of all those guys. This has finite global dimension. And again, the dots, where now you can perhaps start to guess what I'm going to fill the dots in with. It knows, in this sense here, it knows about the representation theory of G. It knows about where R came from. But let me not try to make a precise statement there. Both parts that I just said fail if n is 3 or more. which is to say that finite Cohen-Macaulay type fails if n is at least 3 for these rings. I mean, there are examples of finite Cohen-Macaulay type in dimension 3, but these ones don't have it. However, oh, so let me say that there are other examples of finite Cohen-Macaulay type in dimension 3. And for those, I forgot to give this thing its rightful name. This is called the Auslander algebra. The Auslander algebra still has finite global dimension. But, and here I'm again tempted to put ... but eventually you'll get tired of that and won't let me do it anymore. So let me say one particular thing, that it's not as nice as in dimension 2. In particular, it's not maximal Cohen-Macaulay as an R module, which this one is. So the good news in dimension 2 fails in several senses to ascend to dimension 3. Yes, ma'am.
N bigger than 3, you're saying that none of these rings are invariant have finite Cohen-Macaulay type?
Correct. Sorry, there's one exception, which is the this one, where you send each variable to its negative. This one does have finite Cohen-Macaulay type, but there are no other examples. So, except for that one. Thanks. All right. So let me now, I'm still going to stay with this. I have a little more to say about this Mackay setup. Let me say a little bit about geometry in this setup. So this is, what I'm going to say is essentially Art and Verdier. So let's assume, let's stick to n equals 2. And let's set x to be spec of this invariant subring. So it's some kind of quotient singularity under this finite group action. Then x has an essentially unique minimal resolution of singularities. So I'm not going to define minimal. But as you may know, resolutions of singularities in general are highly non-unique. You can always blow up something more. What this says is that in dimension 2, at least, if you get down to a place where you can't blow up anything more, or you can't blow down anymore, then it's essentially unique. And let me call this, I don't know, call it pi from y to x with the exceptional fiber a bunch of p1s. And these are arranged in some configuration upstairs on the resolution. And one of the things that Artin and Verdier prove is that, make sure I've got all the hypotheses I need here. Right. That there is a one-to-one correspondence between the indecomposables, Maximo-Cohen-Macaulay modules over R, which again in this, just to kick the horse one more time, in this scenario it's exactly the direct summands, the indecomposable direct summands of S, between those guys and those P1s. Which I'm not going to write out, but is relatively straightforward. You pull up M from X to this resolution. It probably acquired some torsion on the way, so you kill the torsion, and then it turns out that its first Chern class intersects exactly one of those P1s, and that's the one you associate to it. So I guess I am going to explain it. So in dimension 2, just to sum up, we've got everything matches. Representation theory of G, projectives over this group bring Maximo-Cohen-Macaulay modules, and this geometric data, these exceptional components. Now, this result of Artin and Verdier has a jazzed up version in terms of derived categories. So let me finish this discussion of the Mackay correspondence with that. So there's a derived version of what I've been talking about. To explain it, I have to say a little more about this Y. So the minimal resolution of singularities is realized in actually several different ways, but the one I want to talk about right now is as Nakamura's G. Hilbert scheme, which I'm going to call H, or more lengthily, Hilb G of C2. And what this is, it's some sort of moduli space. Let me write it a little informally. Let's just say that it is the set of quotients of the power series ring in two variables, which are isomorphic to Kg as G representations. So implicit in here is that I should be some sort of stable under the action, and what you get if you look at it as a representation of G is just the regular representation. So it's not super important, but I want you to know that it has a very concrete description. And then the derived version goes like this. And this is due to Kapranov, Vassaro at the turn of the millennium. And it says that the bounded derived category of coherent sheaves on H, so this G. Hilbert scheme, is equivalent to the bounded derived category of I'm going to write here something I haven't written yet, co sub g of C2. So what is that? That's just G equivariant, coherent sheaves on C2. Well, wait, actually, we have a different language for that. Coherent sheaves on C2 that have a G action, that's S modules that have a G action. That's exactly this modules over this twisted group ring, and this is always. So that S hash G there, that's the guy that I was trying to convince you might deserve to be called a non-commutative desingularization. Yes? Of, well, yeah. I'm not grading anything. This is not a proj. So I think it's okay. So this S hash G doesn't just know about the resolution. I think this theorem, one way to say it colloquially is that it is the resolution. In this derived sense. So that would be one very strong candidate for inserting where those dots were on some previous board, that a non-commutative resolution of singularities should have some sort of derived equivalence of this flavor. And let me, at some point, whoa, where did it go? At some point, G got smaller. It became a subgroup of SL2. Here, I guess. Here. Sorry about that. This theorem requires G to be an SL2, which is essentially the same as R being Gorenstein. So, sorry about that. But the 2 there is what I want to focus on. And the natural question then is, even though this finite Cohen-Macaulay type property fails in dimension 3 or more, one might ask for a theorem like that. All the characters you can still define. I mean, this side of the diagram we always understand. This H, just change the 2 to a 3 or whatever. So in dimension greater than or equal to 3, this thing makes sense. So we can still think of it as a candidate here, but so if n is 3, it's not a minimal resolution of singularities. We sort of lose that entirely in dimensions other than 2. And actually, even worse than that, if the dimension is at 4 or more, it's not even smooth. So even if you got a diagram like that, you would be hard-pressed to use it as motivation for calling this thing a resolution of singularities. So let me tell you the answer, or some answers to this question. Dimension 3, the answer is yes. And this is a theorem of Bridgeland, King, and Reed from 03, I think, no, 01, which is essentially the same picture as on the board above. So now G is in SL3. Then I get an equivalence just exactly as above. Between these derived categories, and then I have this arrow that I always have down the side. So again, I take this as some evidence that in dimension 3, this, which, just to bring it back, is the category of modules over some endomorphism ring, is a resolution of singularities. The key here is, I said that it's not a minimal resolution of singularities, but is what's called crepant, which I will not define. In particular, let me not say that. Let me say something else. Bridgeland, King, and Reed, in that same paper, conjecture that it's really the crepantness that's relevant. So I've seen this attributed to them, also to Reed by himself, also to Nakamura. Let's assume at some point K became C, huh? Bonus points if you can find where it happened. So if I assume G is in SLN, then, and if I further assume that Y to this quotient is a crepant resolution of singularities, then we should get that there's an equivalence of derived categories between these guys. In particular, as I said, A here is important. It doesn't say the crepant resolution of singularities. There might be several. But this right-hand side is constant. It depends only on the data given at the beginning. So in particular, this conjecture would imply that this derived category is independent of which resolution you happen to pick, as long as it was crepant. So, okay, that's 50 minutes on the Mackay correspondence. I could easily do 50 more. In fact, I've said nothing about ADE diagrams. I've said nothing about the finite subgroups of SL2. There's so much more. But all of this was to motivate, from a completely different direction than in my talk last week, the following definition. is a definition due to Vandenberg. So let's let R be a ring of the kind we were discussing. So at some point, G started living in SL2, so I want R to be Gorenstein. Let's have it also be a normal domain. You might ask that it live over the complex numbers if that's your thing. Then a non-commutative Crepant resolution of R, which I guess the snazzy way to write that is NCCR, is an R algebra, lambda, which is of the kind we've been talking about. So it's modeled on this endomorphism ring of S. So first of all, I want it to be of finite global dimension. I want it to be of the form of an endomorphism ring for some module M. And let's go ahead and assume M is reflexive. By the way, this is actually a question that I'll come back to. And finally, and here's one substitute for that dot, 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 let's assume that lambda is maximal Cohen-Macaulay. As an R module. That was certainly the case in the Mackay correspondence because lambda was free over S, and S was maximal Cohen-Macaulay as an R module. Oh, yeah, right, the MCM part. The reflexive is Vandenberg's definition. All of the ways we know how to cook these things up, you can actually take the module to be Cohen-Macaulay. Yes, well, yes. I guess that's going to be from here. R is going to live in the center. I should assume the module is faithful, so it actually, there's no kernel. Reflexives. Oh, no, not equal to the center, no.
There it was, right?
There it was, that's true, that's correct. That's not part of the definition, no. So that is one well-motivated definition. Let me, by the way, this third bullet I kind of sprang on you. Let me say a word about lambda being Cohen-Macaulay, maximal Cohen-Macaulay, as an R module. What I want to say is that there is no general relationship between M being maximal Cohen-Macaulay and its endomorphism ring being maximal Cohen-Macaulay. It's bad in both directions. You can have M being Cohen-Macaulay and the endomorphism ring not, or vice versa. There is one useful criterion which is going to come up probably next time, which is that if X, the X from 1 up to D minus 2, so I guess D is now the dimension, of M against M all vanish, then that is enough to imply that this endomorphism ring is Cohen-Macaulay. This is a very strong condition. It implies all sorts of things. It's actually equivalent if, let's see, what do we need? We need R to be an isolated singularity. Is that right? Yeah. Since I'm assuming that R is Gorenstein, that's true. So let me, in the last few minutes, give you a couple of first theorems about this definition, unless there are any questions. I'm sorry, say again. Yes, sorry. So, correct. So a couple of first theorems. And conjectures. So the first one is, I'll go ahead and give you your whole name. Sorry about that. Due to Vandenberg in that same paper, and this was, in some sense, the underlying motivation for the definition, goes like this. Let's suppose R is Gorenstein and normal. Let's take X to be the spec of R and pi a resolution of singularities. A couple of assumptions on pi. Let's assume several things, actually. Let's assume that pi is crepant, whatever that means. I haven't told you. Here are some things that are a little more down to earth, perhaps, if you don't know what crepant means. Let's assume that the fibers of pi have dimension at most 1, and the exceptional locus has codimension at most 2. This sometimes gets called a small resolution, though that's different from being a small group. Then, put it over here. Then R has one of these. Non-commutative crepant resolutions. There's no dimension assumption here, by the way. Has a non-commutative crepant resolution, one of these things, with the module NCM and an equivalence on the derived category level. If in addition the dimension is 3 with these assumptions still in place, then the existence this is not how I want to phrase this. Let me say it like this. If in addition dimension is 3, then all the Crepin resolutions which I mean these non-commutative ones and the usual ones, are derived equivalent. I think this is a reasonable place to stop. This is the first big theorem. Next time I will try to unpack it a little bit and tell you some attempts to extend it. Then I'll get back to what I promised, which was more concrete examples. Thanks.